Right. Can you confirm that you can see the screen, the PowerPoint?
Yes, doctor.
All right. Okay. So what we are going to do this morning is the first part. We are going to listen to a lecture, and the lecture is entitled Multidimensional Scaling. Okay, multidimensional scaling, and I think it's going to last for maybe 30-40 minutes, this lecture. And after that, we are going to take a short break, maybe around 15-20 minutes. And after that, I will um, demonstrate to you some R codes that we can do on R Studio Cloud. Okay, so the demonstrations will include demonstrations for running multidimensional scaling in R. Secondly, exploratory factor analysis in R, and lastly on the structural equation modeling in R. Okay, let's go to the lecture. So again, the lecture for this week is multi-dimensional scaling. All right. So what is multi-dimensional scaling? Multi-dimensional scaling is a tool. Okay, it's a tool, and by using this tool, you can quantify similarity judgments. Okay, for example, you have 20, 30 things, small things, maybe different color, different taste, and then you give to maybe to 20 people, and you let them sort the small things based on similarity, and that decision is solely based on their assessment. So person A may split the 20 things into different groups. The other will do the same thing. So basically is a tool that you that enable you, not you but the participants or the subjects, to quantify similarity judgments. It is also known as a set of statistical procedures. Okay, a set of statistical procedures that you can use to perform exploratory data analysis and to reduce the dimensions of your data. For example, you have um, lots of data, okay? Especially you have lots of variables in your data set. You may have um, knowledge, attitude, and practice questionnaire. And for each set of questionnaire, you have maybe 20, 30, variables. So let's say we have 20 variables for each questionnaire, for each domain, 20 for knowledge, 20 for attitude, and 20 for practice. Now you have 60 variables. Okay, so by doing multidimensional scaling, you can look at the pattern of these 60 variables. Okay, how many groups together, how many uh, groups you know further away from other groups. So you can see kind of clustering. Okay, clustering. At the same time, you can do um, um, dimension reduction. Okay, dimension reduction from 60 columns or 60 variables. You can look at, or you can identify three or four main groups. So other variables that don't fall into these three or four main groups can be excluded from your analysis. Okay, that is dimension reduction. Um, so again, this is another definition. It's a technique. Okay, it's a technique, uh, and this technique can create a map. Okay, a map. Imagine you have a map, and in the map you can see locations of objects that you are interested to assess or examine. Okay, so you imagine you have a map in front of you, and you can see dotted or dots of the things you want to measure. For example, that variables, 60 variables, and see where they clumps together. Okay, how many clumps can you see from the map? So basically it, and you can also create a table. Okay, a table, and the table can show you the distance between the variables that you are studying. For example, you have um, variable p1, p2, p3, p4, p5. So you can see the distance between p1 and p2, p2 and p3, p1 and p4, p3 and p4, so on and so forth. So you can measure this on the map. You see, you can plot this p1, p2, p3, p4, p5 on the map. Imagine you have a map and you see the dots on the map that represent p1, p2, p3, p4, and now you measure the distance of each pair, p1 to p2, p1 to p3, p1 to p4, p3 to p4, and so on and so forth. By doing that, you can see which pairs sit or stayed near, and which pairs stayed far away from the rest. So basically you can see where which of the variables uh, have what we call as sameness. Okay, sameness, kesamaan. Okay, and which variables display dissimilarity. Okay, perbezaan. Okay, so this is one example of a table that you can generate from multi-dimensional scaling. Sorry. So this is another example where I took this from a web page on GitHub, where you can this is a map, a 2D map, where you can see points, locations, and from here you can see clusters of possible clusters, because you don't know yet. Okay, exactly, are they clusters or not? But it seems that that there are points that are clustering here, there are points that are clustering here, and there are points that are clustering here, and also maybe this one, but not so much here, right? So you and when you look at the data in more detail, then you know that these are basically belong to the colon data. This belongs to kidney data. Sorry, colon here, right? Colon, um kidney, and also liver. Okay, so do you see two clusters, or do you see three clusters? It ups to to you as an analyst to ascertain, okay, uh, or to decide on the number of their clusters. So basically, it has a little bit of subjectivity, even though this the point can be measured quantitatively. So that's why it is called as an exploratory data analysis, because you want to explore. Okay, you want to explore, you want to identify if there are possible clusters, or it can be used to identify unrecognized dimensions. So from here you can see, okay, there might be two dimension, okay, this dimension and maybe three at this dimension and these dimensions, or maybe this dimension and this dimension. Again, you must decide on the number of dimension. And you can also obtain comparative evaluations of objects. um when you look at the map the methods of analysis for multidimensional scaling, then this is the common way of presenting the results from multidimensional scaling. It is in a form of map, okay, where you have axis 1 and axis 2, or dimension 1 and dimension 2. And then the map spatially conveys the relationship between items. So where you can see that similar items are located nearer to one another, and items that are different are located further away. So this is a website that you can go to. From here you can plot the map, and you can hypothesize that this belong to a group, this belong to a group, this might be this might belong to another group, and a few of them might not belong to any group. Okay, again this is a map, and the map show the locations between uh, each of the point, but similar items will be grouped nearer to one another, and different item will be grouped further away. So you can have, like, maybe one, two, or three, or even more dimensions. Okay, for example, they may, one dimensions might be, only the color. Two dimensions, maybe they are similar according to the color and the taste. Maybe if you got three dimensions, certain things are similar because of the color, because of the taste, and because of the price. Maybe, for example, if you take chocolates, right? um, Chocolates, so you may group different chocolates into different groups. Maybe one based on the taste alone, one dimension. Maybe based on the taste and the price, two dimensions. Maybe on the taste, the price, and the packaging, three dimensions. Maybe on the taste, one, price, two, packaging, three dimensions, and the fourth dimensions from where the chocolates are produced. But the more dimensions you go, the harder to classify things. Okay, so it is much easier to use computer program to calculate this metric or non-metric solutions. And how do we present? Again, we present using the map, or the map or the proximity matrix. Okay, proximity matrix. So this is an example of um, again, you need to, a proximity metric is required. I think in the demonstration I'll show you how proximity metric looks like. So if you have, like, um, things, um, for people to group, okay, to group or to find similarity or dissimilarities, how many pairs would you require? Okay, would you require? So if you have, uh let's say we have chocolates, 10 brands of chocolates, right? 10 brands of chocolate, A, B, C, D, E, F, G, H, I, J. Okay, so how many comparison or how many pairs you need to have? So you just replace this K with 10. Okay, 10, 10. So 10 minus 1 is 9. 9 divided by 2 is 4.5, and 4.5 times 10 will be 45. So if you have 10 chocolates that you want subjects to pair, then you have to have 45 pairs. Okay, A with B, A with C, A with D, A with so on and so forth. B with C, B with D, B with E, so on and so forth. And from there you can, um, look at, how many dimensions you can produce. Okay, okay. So this is based on only one dimension. For example, when you say to subjects, okay, find similar chocolates according to taste only. Okay, that's one dimension. Two dimension, you say to them, okay, find or groups chocolate based on the taste and on the price. Two dimension. Okay, and then you add more dimension, 4, 5, 6, 7, and so forth. Okay, if you look here, um, the more you go, the more you go, the stress level is less. Is less. It means that it is easier to to what we call to groups. Okay, to groups. The um, if you have more choices you give to people, then it is much easier to group. Kan? Okay, this is some of the example. Okay, in case one. Okay, suppose you have 10 people. Okay, 10 people, and you ask them to rate similarities of 6 cars. Okay, so because there are 6 cars that you want them to find similarities, how many pairs they need to do? Sorry, I've got a little bit of coughing. Okay, so six minus 1, 5. 5 divided by 2 is 2.5, and 2.5 times 6, you got what? 2.5 times 6, 12, 13, right? Okay, I pun tak ingat sorry for that. Okay, there's someone. Okay, right. So let's see, 6, how many comparison must we do? 6 minus 1 is 5. 5 divided by 2 is 2.5. 2.5 times 6 is by 6, 30, 6, 5, 3, 12, 15. Okay, 15 comparison of 15 pairs. Then you can ask them, okay, when they compare this six car, A, B, C, D, E, F, A and B, A and C, A and D, B and C, D and E, so on and so forth, and you ask the subject to rate from scale 1 to 10. 1 means that the cars are identical in every way, and 10 means that the cars are different as possible. Okay, then you can average the ratings, and this can form a similarity matrix. Okay, at the same time, in addition to similarity matrix, you can have also a map, a scatter plot of the locations of the six cars. For example, oh, I don't include the map. All right. Um, Example number two. Okay, this is where you have a set of sound. Okay, a set of sound. You have a dentist drill, and you have waterfall, and then you have I think sound from constructions, sound from other things. So you have a list of sounds, and then you ask the subject to rate the similarities of the sound. For example, in this case, the pair is between dentist drill and waterfall. So you ask the subject, could you rate from the scale of 0 to 7? 0 means completely different, and 7 exactly the same. You know, how similar dentist drill and waterfall. Okay, and then you ask the subject to do dentist drill with maybe sound of TV, dentist drill with sound of motorbike, and then sound of motorbike with waterfall. All possible pairs. And you can um, do this this, so this is the metric that you can have, and this is the sort of the map that you can produce um, from the data analysis just now. So from here you can see that A is near to B, but far from C and D. Okay, it means, so at the same time it means that B is also far from C, and B is also far from D. Okay, so by doing this, you know that A and B is more similar compared to A and C and B and C and B and D and C and D. All right. Um, in case three, this is um, a map again. Um, and in this case, you ask the subjects to rate the similarity between hockey and football. Okay, and then um, croc, croc, cricket and tennis, golf and baseball. So, what the subject will do is that they will compare, or they will rate the similarity between golf and cricket, golf and tennis, golf and hockey, golf and football, golf and basketball. Basketball with golf, basketball with hockey, basketball with football. And they have to rate similarity for each pair, and then you can map the pair on this map, which has dimension 1 and dimension 2, a 2D map. And you can see that hockey is almost similar to football, and cricket is almost similar to tennis. But golf is, somewhere up there, and basketball is somewhere up there. So you can see maybe, like one group here, one group here, one group here, and one group here. So how you test if the analysis is good? Okay, so you can do a test, a goodness of fit test for multidimensional scaling. So this is the where dij hat is the predicted distance, and d is the observed distance. Okay, so if the um, location of this distance are bigger, then you have more stress lah. It means that it's getting more and more difficult if the distance between the observed and the predicted are larger. How about the number of dimensions? Again, the number of dimensions will determine the similarities and dissimilarities. So, as an analyst, you need to anticipate, whether it has two or three or four or five dimension. Usually, it has at most three dimensions. Okay, beyond that is quite difficult to do. Case number 4 is, a rate of dissimilarity of two subjects. So you can rate dissimilarity and you can rate similarity. It's just, same thing. Okay. So for case number 4, rate dissimilarity between two objects, and how to do that? You can use a 7 or 9 point scale. Remember the example that I show you just now with the waterfall and dentist drill. Okay, this is 7 unit scale, but you can have up to 9. So let's say you have 12 stimuli or 12 tests. So 12 times 12 minus 1 divided by 2, 11 to 5.5 times 12, you got 66 pairs that the subjects must evaluate. So you give this to 77 participants, and then you can have these two results. Okay, this is the proximity matrix, and this is the map. Okay, and multidimensional scale map. So this is circular saw. So the subjects rate dissimilarity of sound. So they were given the sound of circular saw, gargaji, dentist drill, fan, hoops, um, howling wind, ship's horn, stadium, stone in well. So and the subject must rate the dissimilarity between circular saw and dentist drill, circular saw and fan, circular saw and hoof, dentist drill and what fan, dentist drill and hoof, so on and so forth. Okay, if you look here, circular saw is very similar to dentist drill. Okay, and waterfall is similar with circular saw, um, stadium and number six. 1, 2, 3, 4, 5, 6. Stadium and um, ship's horn, okay, are similar, right? Okay, 9. Ship's horn and number 4. 1, 2, 3, 4. Ship's horn and hooves are very, very different. Okay, are very different. And then what about this one? Okay, um, number 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Waterfall and typewriter. Okay, waterfall and typewriter is also very different. Okay, so from this proximity matrix, you can draw a map, and then you can see, there might be, there is one group here, there is maybe one group here, and there is maybe one group here. Okay, right. So this is this is a test from environmental sounds. 37 participants. Okay. um so you can average the results from the 77 participant or subjects. So what you do is you do aggregate multidimensional scaling. So you can see, see a circular saw, dentist drill, um, fan, hooves, um, bowling wing, ship's horn. They are in this group almost similar among them. But you have TG. TG is what? Tire and gravel. HO is hoops, and TY is typewriter. They are, clustered in one group. And you have WA, wasp, and SW, which is stone in well, quite further away from the other two groups. Okay. But if you ask me, I mean, what's the use of this sound study? Um, I can't comment. Okay, I'm not an environmentalist, so you have to. But this is how you do multidimensional scaling. Okay. Um. All right. So this is individual difference scaling. I think this is a bit complicated, so we'll skip this. But what you do want to see is um um whether using the individual difference scaling, okay, is can you can you see the clustering of the sound, okay, and of course you can see here one and two and one and two here, right? And from here you can identify who are the different subjects. Okay, this from here you can see um, the sound, and here is the map of the participants. So you can see that most of the participants are similar, but there are participant 31, 36, 55, and 73 who are a little bit, who are not similar from the rest of the 77 uh, people. Okay, so yeah, so this participant put less weight on two dimension than the rest of the sample. And so what we have gone through is basically the concept of multidimensional scaling. And what's next? Next, we are going to do some analysis. Okay, and these are the links that will be useful for you to run multidimensional scaling. Okay, in R. So I have so I have 1, 2, 3, and 4 for examples of how to do multidimensional scaling in R. So yeah, references. There are two references I will give later, which I think are easy to read. Okay, the one is the multidimensional scaling by Mary Mulgavin, and the other one is multidimensional scaling by Michael Hood et al. Um, this one is much easier to read, shorter, and this one longer and more difficult to read. But you know, I hope you read these two papers. Okay, read this one first, and then after that read this one. So I guess that's all for the lecture. We'll take 30 minutes lah, 30 minutes break. Okay, so we'll come back. No, 20 minutes break. Okay, 20 minutes break. We'll come back at 10:10. Okay, so at 10:10 I will show some demonstrations on R. Okay, on R. So see you um, at 10:10 a.m.